Could you confirm that the slides are visible?
No. It's on the example page.
Okay. Now?
Yes, it's okay.
Perfect. I want to verify also the full screen mode. Could you see the full screen?
No.
The
I think if you put on the full screen, it's freezing.
okay. Now? Now is okay?
No. Can you change the page?
Now?
No, it doesn't change.
Now is okay?
Yes, it's okay.
Scrolling?
Yes.
Perfect. Okay. Now
Thank you.
I will welcome. Different marker. Today we are going to discuss the last part of our power system operation and control. And today I'm not going to give you more problems, only some mathematical models which you can directly implement in MATLAB or other softwares which are you are familiar. And MATLAB is the most easiest way of implementing these complex equations. And already I uploaded some examples how to use a one area control, two area control of your power systems, MATLAB Simulink modules in the previous lecture with some description of the simulation model are available in your canvas for downloading. You can try if you have a MATLAB. So today we are going to discuss how to model your hydropower plant. Here I like to give you a brief formulas, not the derivation. It's not important for you. The final transfer function is very important so that you can able to make your hydropower plant or you can make your power system using steam power plant or whatever the types of turbine you want to use. The model is the same. The concept is the same. Only the turbine is going to change. If you are going to use wind turbine, it's wind. If you're going to use a hydro, it's going to be fluid. If we are going to use coal, it's going to be a steam turbine. That's the only difference. But other aspects of these power system modeling is the same. So today we are going to look at something how we can able to model a hydraulic turbine, how to control its speed governor system. It's very important. And I'm not discussing on thermal power plant. If you want to learn thermal power plant, your textbook is very vast. You can find the modeling, how to make a steam turbine. Everything is available in your textbook, but our goal is on hydropower plant. So I restrict myself with my presentation on hydropower plant. And of course, very important at the end, you have to be good in your electrical machines because basics from the bachelor degree, electrical machines. At the end, your power generator is a synchronous machine. So the same equations, same calculations we use for modeling. There is no difference. If you are could revise your basics of synchronous machine, today's lecture is nothing. So we are going to discuss today about Parkes transformation and important aspects of swing equations of your synchronous machine. modeling of speed governed system with limiter. That's very important. I will introduce a term called limiter. You can also see in your simulation blocks. Today, I will show you some examples and the effect of excitation variation. So how you, if you change the excitation, how you can control your synchronous machine. So I believe you know what is the meaning of excitation. So in synchronous machine, you have armature winding and field winding. What is an armature winding? Armature winding is a rotating part of your machine. And field winding is an electromagnet, where you try to create an electromagnet by using DC power supply. You apply, increase the excitation, decrease the excitation. If you increase the excitation, your voltage will build up. When you are reaching the rated excitation, you get the rated voltage. If you are not giving excitation, what happens? Synchronous machine will generate some voltage, but very minimum, very minimum. It will not go to the rated value. So excitation is nothing but you are increasing the magnetic field, electromagnetic field. The electromagnetic field is directly proportional to the output voltage. I don't go very inside the dynamics. I'm giving an outline. So there are three types of prime mover. We have different categories. One is a primary control, which is called speed governor control. Secondary control is called load frequency control. We already seen many LFC methods in our previous lectures. And third one is called a tertiary control, which involves economic dispatch. So this is the complete modeling of your power system. So if you want to model a power system analytically by using softwares, there are only three parameters you have to look. One is your primary control, secondary control, and tertiary control. How about hydraulic turbine? There are different types of hydraulic turbine you have for developing your hydropower plant. It all depends on your head. So we have three types: low head, medium head, and high head. How to decide? If you are going for a low head, it can go up to 100 inches height. You can have a look 100. What is the speed? You can go between 90 to 180 RPM or 100 to 40, 100 to 400 RPM. So it varies in the range. These ranges, you can have a variation. And what type of propeller is used is a reaction turbine, one type. For the medium head, which is between 50 to 1000 height, then the speed variation from 90 to 200 RPM in case of 50. In case of 1000, it can go up to 100 to 400 RPM. Please note, in electrical machines, small machines, when the size is coming down, speed is very high. When the size of the machine become very large, for example, hydropower plant, the turbine and the machine size is very big, more than this hall. If you go to the real power plant, the armature of your rotating part of your electrical machine, which is a synchronous machine, will be 2 times this hall. Then think the size is very big, I'm right? As the size increases, weight increases, everything increases in the machine, I'm right? So the speed comes down. So if you want a high speed machine, either it is a synchronous machine or asynchronous machine, induction machine, the machine has to be small. So when small machine, high speed, large machine, low speed, that you can be able to see here. So 100 to 400 RPM is the possibility. And what type of turbine they use is a Francis type turbine. It's a special purpose turbine. If you're going for high speed, you can go from 800 and above height. You can see the speed now. It becomes 3 to 7 RPM. This is the speed. 3 to 7 RPM. As the size increases, the speed calms down. And yes. I head, as the head increases, the machine size has become very big and you are generating a large power. That case, the speed comes down. So you can't. I put it wrong. Sorry, it's a head. Sorry, it's a head. Is it? I made a error here. So head. So you can have a speed between 3 to 7 RPM and speed is 120 to 720 RPM. This is the possibility. And what type of turbine we use is the Pelton wheel. So these are the three types of hydraulic turbines we use in practice until now. There is no more advancements. So these are fixed now. Where the power system we are working more on digitalization, loss consumption, integration. So the power plant are not changed. Infrastructure of the generation unit is the same. We never change because it is done 100 years before. Where we are working more, we are working on making the power system advancement with the technologies on integration, reducing the losses, fault tolerant capabilities, load sharing, economic dispatch. These are the modern aspects we are working more. Because if you want to build a new generator, it's again a large investment. So these generators are done 50 years before. So, or 100 years before. We don't want to change them. Then this is an example how you can make a model of your hydraulic turbine system. And you can have a look. You have a dam. Before the dam, you have the forebay, the flow for the water. Then you have a penstock. The penstock can have a look. So from the penstock, it goes to the turbine. So based on the speed and the level at which the head reaches the turbine start rotates. And for this purpose, we keep the height from the penstock to the ground is h. The height from the forebay to the ground is h tau. So these are the some specification you have to look. I'm not going inside with the derivation. The final result is very important. So let L be the length of the penstock in meter. Q is the discharge of the water in meter cube per second. And small v is the velocity of the water discharge meter per second. H is the operating head in meter. Then we are going to look at some terminologies we're going to introduce because these flow of water is not fixed. That's a big challenge for electrical power engineers. So we are going to have a delta X in per unit, change in turbine gate opening. So you have a turbine gate opening that we keep a small change. We are only introducing all these parameters, delta X and delta Q be the per unit change in water discharge. So don't forget Q means our mind goes for a reactive power. In hydro power plant, Q also represents the water discharge. So delta Q is a small change deviation in your water discharge in per unit. And delta T is the turbine torque. So whatever the turbine, you have the torque, which is produced by the synchronous machine. Small change because you have a small change in discharge of water. That small change in water can make your turbine to have different torque. So the small torque change we use delta T. Now delta H divided by delta Q. We are finding the ratio of small change in the operating head as a ratio with respect to change in discharge water, which is given by 1 minus Z into 1 e power minus 2 tau E into S divided by 1 plus e power minus 2 tau Es. So tau E is an electric time constant of the system. So it's a time constant. Usually we will design it based on calculations. There are procedures to design this one to find an appropriate values. Then if you look at the equation, the ratio of change in head to the change in water discharge is directly proportional to Z. Directly proportional to Z. What is an Z? Z is a impedance of your penstock, normalized impedance of your penstock. And I said about time constant, which is an elastic limit of the penstock. So time constant delta E is the elastic limit of penstock. And S is the complex frequency. So why we make all the system in S domain, in Laplace domain, because you get in terms of frequency. S is equal to j omega. So S is a complex function. So you get tau plus j omega. So that periodic, because we are introducing a term called delta H, delta Q, a small deviation. This is with respect to the time. So we consider as a frequency. Done according to the first order pad approximation through mathematic approach. So you might be studied in your mathematics what is a pad approximation. So I'm not going in detail. If you apply a pad approximation with the above equation, so you know what is pad approximation. E power minus x is given by 1 minus x by 2 divided by 1 plus x by 2. Now, with respect to our ratio of change in head towards change in small change in discharge, if you substitute this value, you get minus s into tau w. So now this ratio is directly proportional to your s function. Directly proportional to your s function. Directly proportional to your s, also directly proportional to tau w. It's again a time constant, but we give it different terminology. So here the time constant tau w is called as water starting time or water time constant. So you can easily calculate if you know what is tau w, and S is given by again delta plus JW. So you can easily calculate what is the ratio. Then another important thing in terms of in detail approach, how to calculate your delta Q. So delta Q is given by A11 into delta H, A1 into delta N plus A13 into delta X. How to calculate delta T? Delta T is calculated by A21 into delta H plus A22 into delta N plus A23 into delta X. You don't worry about the derivation. If you look at the derivation, then it's up to you to decide. If you want to learn these design in detail, you can look the textbook. You can understand please understand when and how we develop experts. Experts are not created in one day. If you want to become expertized in one particular subject, you should have a clear vision on the analytical part first, then the execution part. If you want to learn as an application, then look at the equation is enough. So if I want to calculate delta Q, this is my equation. If I want to calculate my delta T, this is my equation. Then if I look at the each variable, how to calculate, we have the direct formula. So we have different constants, which is A11, A12, A13, A21, A22, and A23. How to calculate A11 is a partial derivative of your change in water discharge with respect to the head, change in head. If you calculate this one, you can be able to find what is A1. Similarly, A21 is nothing but a partial differentiation of delta T divided by delta H. If you want to calculate what is your A12, partial differentiation of your delta Q divided by delta N. Similarly, A22 you can be able to calculate A13, A23. So the formulas are directly given to you. You apply the formula, you calculate the values of these constant and apply here, and you can calculate what is delta Q and delta T. So the change in turbine torque due to the change in the speed. Why you get a change in speed? Because you have a small change in the discharge of water. The water which enters into your turbine through the penstock has a small change in the flow rate. So that's why you have a change in the torque. So in order to calculate these changes, already we have the equations and we consider the speed is relatively very small changes. We need to optimize everything in order to make the equation more easy without having complexity. So we consider this change in the speed is very relatively small. Then you're going to have only the constant. You can reduce this delta Q equation into A11 into delta H plus A13 into delta X. Similarly, delta T can be reduced to A21 into delta H plus A23 into delta X. Now you can be able to find the ratio between delta T to delta X, which is given by this equation. So you need to know only this equation in order to model your hydro power plant systems. Can I go to the next slide? For a ideal turbine, now we are going to enter into the system. We have seen different time constants, variables, how to decide modeling. That's very important. How to model in mathematically in a simplified fashion. So in case of ideal turbine, you can take the variable A11 as 0.1 into x naught, A12 equal to 0, A13 equal to 1.0, A21 equal to 1.x naught, A22 equal to -1, and A23 equal to 1. So this is the ideal condition. For an ideal turbine, you can directly take this value and you apply in the equation delta T divided by delta X. Then your equation become, this is the reduced one, the reduced equation. With this reduced equation, if you are going to have a full load condition, if you are going to have a full load hydropower plant, your hydropower plant is going to be fully loaded, then consider x naught equal to 1 per unit in this equation. Then substitute that value. You can further reduce the equation delta T divided by delta X is equal to 1 minus tau W into S divided by 1 plus 0.5 tau WS. So this is the complete equation of your delta T divided by delta X. Now I'm going to make it like a transfer function. You already know what is a Laplace transformation. Laplace transformation of output divided by Laplace transformation of input. So if you take this is the output and this is the input, then this is going to be your Laplace, transfer function equation. How to bring this equation in real application in MATLAB or Python or whatever the software you use. There are many softwares in the world to analyze. Most commonly, we use MATLAB and Python. So in this case, you can able to have a linearized model of your hydraulic turbine. How to make a linearized model? Already we see in the equations. So you can apply that equation in this model. So your input is PGV and your output is a mechanical power. So input is a flow of your water and you get a mechanical output power as a rotation. In order to make a linear model of ideal hydraulic turbine. So this is a generalized model, but if you want to consider loss free and I want to make a simplified model, then I can use this model, which is I derived here. So this is the model non-ideal condition, dynamic condition, the real effects, all the parameters is considered. This is the model, which is ideal model without considering the losses, etc. So that's why this is the ideal hydraulic turbine modeling. So if you use this equation in your MATLAB, you have a transfer function. You can take the transfer function. You can directly enter the value of TW, it's finished. Then you give the input, you get the output, which is going to be a realistic ideal model. So in this case, what is PGV is the input to your hydraulic turbine given from the speed governor system. For example, what is the value of your TW? That's very important. So the value of TW, you can't, I tell you something, you refer any books in the world, IEEE books. What is the uniqueness of this book? I'm not promoting this book. You can't find all these details. This is the difference between some teaching methods in Indian scenarios. We give more details because we want the students to develop the projects. So we give all the values, how to model the system. So in this case, you can refer any IEEE books. You can't find, they will not give you how to design. Nobody will give you. Because they can't explicitly given because it's a part of the research. So if you have a research team, these books can be developed. Otherwise, it's very difficult. In real time, I'm giving a real scenario. In my experience, I worked in Aalborg University. They developed many books on wind turbine because one of the major projects, major research in their institution is wind turbine and power electronics. So their books are more research based. You get more ideas. The solutions will be like a ready-made. So the students can easily get all the ideas and they can develop for their research. So getting a book which is giving you all inside parameter, very limited in this world. So for example, how you can fix this value? So this value ranges between 0.5 seconds to 5 seconds. So it varies, depends on your turbine. The limited value is 0.5 second to 5 seconds. What is the typical value you have to use is 1 second. So I have 1 second, 1 second. I designed the model for my turbine, which is ideal. If I want to go for non-ideal model, I have to calculate what is A23, A13, A21, A11, A23. Again, in the denominator, we have A11. And I already given you the formula how to calculate it. Put all the values. If you have the real hydro plant parameters from the hydropower plant operators, you can easily calculate all this. You insert the value and you have to introduce a typical value is 1 second. Then the model is readily available with you, and this model will behave as like the real hydropower. You don't want to test it in real time. This is called dynamic modeling. It's clear to you? And this is ideal modeling. Then how to calculate the power generated. Now one by one we are coming. How to calculate your power generated by the power plant in terms of your time constant. Here the critical time constant is your water. If you're going to take steam, your time constant is steam. For coal power plant, you have to use this time constant. Application is the same. Then I can able to calculate what is my tau W, which is the time constant of your water, 11.8 PL divided by H square into AEG. Or another equation we have 0.366 into PL divided by HT square into AE. So this is the equation we use to calculate the time constant practically. If you know all these values, you can substitute and you can calculate. Now, how to calculate your power generated, which is given by V into HT, AE divided by 11.8. What is A? Average area of your penstock in meter square, and E is the product of efficiency of your turbine and generator. Then I can able to say what is my E, which is the product of your turbine efficiency into efficiency of your generator. So complete model is readily available with you in a very, very simplified equation. Can I go to the next slide? So we finished speed governor part in a very simplified equation. We already brought it into you. Please note a first order system, an exponentially increasing function, a low pass filter. We made the complete speed governor system of your hydropower plant into a first order system. So analyze become very easy. Now, these are the basics of your synchronous machine. I'm not going very much inside. So all the machines what we use in hydropower plant are three-phase synchronous machine. Why it is called synchronous machine? Because it run at synchronous speed. How to calculate synchronous speed? 120 F by P. Yeah, F is your frequency and P is your number of poles. So we have two types of synchronous machine in real time. One is salient pole and non-salient pole. I'm not going inside. So if you have a hydropower plant or wind turbine or any power plants, all our generators are synchronous machine. And we have only two types, salient pole and non-salient pole based on the construction of your rotor. Then how I want to model this machine, how to do that. So this is a simple example. I have three windings, phase A, phase B, and phase C. So each winding will have a voltage induced EMF voltage VA. So for first phase, VA is given by IARA into the derivative of your lambda A. Same applicable for phase C and phase B. If you could slightly revise your basics of electrical machine, the same equation, there is no difference. Then this is the rotating part of your machine, armature windings. We have three phases. And this is the field excitation. I talked about your electromagnet where you apply DC voltage. This is the field excitation, and the field excitation impedances are given here, inductor and resistor. Similarly, the armature reactance, the resistance and reactance are given for the three phases. Now I can able to calculate how the field excitation can be governed by an equation. So in order to calculate the field excitation, it is given by IF, the field current, field resistance, plus the differentiation of delta F. So delta F is your flux linkages. So delta is a flux linkages. So this can also be given as IR plus d by dt. Delta is given by Li, your inductance into the current through the inductance. It's clear? Very simple equations. So now I know how to do the calculation for my field excitation. I know how to do for my three-phase windings. I have the equations. In case of practice, what we do, we consider the system is balanced, but it's not true. In real time, the three windings of your synchronous machines are not balanced. There will be a small deviation in the total impedance. For example, the phase impedance of first winding, say I'm giving an example, 10 ohms. The second phase will have 9.9 ohms. Third phase will have 9.2 ohms. This deviation will make a big difference in the voltage because we are measuring the voltage not in small scale, megawatt, megavolt, MVA. So very large. So small deviation, you multiply into MVA. It's big. So in order to make our analysis very simple, we are going to take a practice that all the three-phase resistance are absolutely balanced. That's why we take RA, RB, RC equal to R. Then your flux linkages is L into I. That's why you make Li here. Because you have the excitation system, but you have three different windings with three different impedances. So obviously this will have different induced EMF, this will have different, this will have a different. In order to make the equation simple, we are considering like this, but in practice it's not true. Can I go to the next one? Then these equations, I didn't go for derivation, is not required. These are basics of your electrical machines. So I take only the important equation. So I'm looking at what is the flux linkage in phase A, phase B, phase C, and this is due to the field excitation. So we have four equations, how to calculate. You can have the formula here. This represents the inductance of the phase A. This is the inductance between phase A and B, and this is the inductance between phase A and C. Subsequently, the currents in all the three phases and the field. So you can use these equations directly to model your system. So even if you are using the models, you should know the final result. Otherwise, you can't understand where to look the parameter. You have a model in your Python, or if you have a model in your MATLAB, or if you have a model in your Power Factory, what are the software you use? You want to look what happened to the flux linkage. If you know these terms only, you can be able to calculate. You don't want to know the equation, but you should know the terminologies. So look at the equation, just keep a note on terminologies. Then how to calculate the voltage? We already find the voltage IR into D delta divided by dt. Now you substitute all these parameters. I didn't go for the derivation. You can see the textbook how to derive it. So if you substitute all these value, finally this is my equation. So if you look at the flux linkage is expressed, and the voltage is directly proportional to your I into RA. Also, it is proportional to the rate of change of your inductance and current. Or I say this is an impedance. I'm right. Current into inductance is impedance. Now I want to calculate individual voltages across the three phases. How to calculate? You can use the equation. This is a generalized equation. Substitute A for phase A, B for phase B, C for phase C, and F for your field excitation. It's clear to you? So I find four equations. Now why I'm doing all these equations? To bring it in the form of a matrix. You know state space analysis. I don't know, you studied control system? Yes, in control system, you might be studied X, A, B, and C matrix. I'm right. So your input matrix, your output matrix. I'm right. Same. That's why we derive this equation. And in generalized form, what I'm going to do, I'm going to introduce as a matrix. In the matrix, I can able to calculate what is my V. This is going to be a one column matrix, varies from A to C. All the voltage parameters I will take. Second matrix, I'm going to take current parameter, which is going to be my all the phase currents and field current excitations. And third matrix is my resistance, which is going to be a n cross n matrix, which is going to have a diagonal value only my resistance. If you look at the diagonal, it's going to be a resistance. Don't ask me why you take like this. You substitute all this here, you will get this equation. That's why you choose column matrix, you choose a column and row matrix. Then what is a delta? Flux linkages is very important here. So we take it as a one column matrix, which has all the three phase flux linkages. of course, field excitations. It's clear to you? Now I model my complete electrical machine into 4 matrices. Now I can take this matrix. If I know the value of all the resistance of the 3 phases, if I know all the values of the voltages, if I know all the values of the current, I can easily model the system in my software and I can analyze without going into real time. Why we are doing this model? Can you tell anyone? What is the reason why we are developing these models? What is the purpose? Yes. Why you need to have these equations? I can design directly. I go to the field, I make the machine and I can do that. Why we want this equation? No idea. Again, the basics. Yes. 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 Very good. Your answer is fine, but it's not the aim. For example, I want to develop a 100 MVA synchronous machine. How much money I need to invest? If I design the machine without doing any testing on the software, I say the efficiency will come 98%, but it's not true. In real time, I don't know what's going to happen. That's why we do a pre-testing with the software. Already you studied in your basics in bachelor, open circuit test, short circuit test. Why are doing that test? For a synchronous machine or asynchronous machine? Of course, for the DC machine, we do the testings to model the electrical machine before it is manufactured. You predetermine the efficiency, you predetermine the losses, you predetermine the performances for a particular application. You do it everything analytically to understand the complete dynamics of the electrical machine, how it will behave when it comes to the manufacturing outlets. If I directly go for the manufacturing, who knows? How do you validate the performances? So if I'm getting a percentage like 99% in software, definitely it will be 98 or 97% in real time. It's clear to you? That's why we make this model to predetermine the efficiency, losses, performances, of course, reliability and lifetime analysis of a large machine in a software environment before it is manufactured. Or if you have a machine, you don't know what to do it, you need to go for the testing. So that's why we need models. It's clear to you? Might be in control system, you heard about, I don't know, MRAS, model reference adaptive system. Because if you have the model and the real machine or any electrical system, you doesn't have any information, but you can make that electrical machine, it can be a motor or something, as per your model. You develop your model, you know the behavior. So the external real-time system will behave with respect to your model. That is called model reference adaptive systems. So we need adaptive system. That's why we are developing all these equations. It's clear to you? I given you very basic, even for a non-technical people, they can understand. So you need a model in order to make your system to your behavior. What you want the performances. For that you are modeling. Now I want to make the flux linkages model. How to make the flux linkages? It's delta equal to L into I. Then I need two matrix. One is my inductance matrix. You can see the inductance matrix, which is a symmetrical matrix with 4 columns and n rows. You can have a look here. Similarly, I have flux linkages. Then it's going to be L into I. So I can easily model any system. It's clear to you? Then we are going little inside the system. You know, all these machines are 3-phase. It's easy to analyze 3 vectors or 2 vectors, which makes you more comfortable. When you reduce the burden, you'll get more comfortability in analysis. So instead of having 3 variables, if you have 2 variables, it's easy. In your hydropower plant, what is your goal? You need to maximize the active power, minimize the reactive power, increase the efficiency of the power delivery. This is the general goal, I'm right. If you have three variables, I give an electrical machine to you. I give an electrical machine, which is an hydraulic turbine, I give to you. I ask you to, yes, maximize my torque, maximize my active power. What you will do? How do you do? Which parameter you have to control? You have a three-phase voltage outcome from the machine. Yes, I have the yes, I get the power, but what I have to do? That's why we go for a particular transformation is called Parkes transformation or Clark's transformation. What is the difference between Parkes and Clark's? If you have a three-phase variable, it can be a current, voltage, frequency, whatever the parameters. If you have a three parameters, if you use these mathematical transformation, in the output, again, you will get three variables. Three variables, again, you get three variables, which is called a D, Q, and 0. D controls your active power, Q controls your reactive power, and 0 controls homopolar components or zero sequence component. Since we consider all our balanced machine, we don't look in textbook for zero sequence component, but in real time you will have zero sequence component because no electrical machines or no transmission line is absolutely balanced between three lines. There is a small deviation in their impedance, and this can create zero sequence component. If you'd have seen my previous lectures with the power system analysis with power quality, I had given all these details. If there is a small change in the three impedance of your system, your voltage will not be balanced. There will be a small difference in the voltage. For example, 400 volt line to line, one will be 399, another will be 400, third one will be 394 or something. I give an example. So this unbalance will come if you have a zero sequence component. So by using this transformation, if I control Q, I can control active power. If I control as a D, active power, Q, reactive power. If I control the 0, I can control zero sequence component. I'm right. That's why these transformations comes into the picture. So one is called Parkes transformation. In Parkes transformation, all the three-phase AC voltages and current, which is instantaneous with respect to time, will be converted into DC component. So the output of your transformation will be a pure DC. You'll have a one DC for Q, one DC for your D, one DC for your zero sequence component. It's clear to you? If you use Clark's transformation, your input is a voltage, your input is a current, three phase with 120-degree phase shift. Output, again, it will be AC, but the phase shift is only 90-degree between D and Q. In order to give a differentiation, we call it as alpha and beta. So D is like alpha, Q is like beta. So alpha controls active power, beta controls reactive power in Clark's transformation. Only difference between Clark's and Parkes, in Parkes, output is DC. Your AC component is converted into DC. In Clark's transformation, your AC component is converted into AC component, but the two components which controls active power and reactive power are phase shifted by 90-degree. Whereas in the input, it is 120-degree. I'm right. This is the only difference. If you control alpha, you control active power. If you control beta, you control reactive power. It's clear to you all? Now look at this one. We are going to discuss on a three-phase winding. So we have a three-phase winding, and now look, three phases of your synchronous machine. And each machine you have output voltage VA, VB, and VC. We fix an axis. You can have a look. This is my D axis, and this is my Q axis. They are always phase shifted by 90-degree, and you rotate it. So this is an example. Say at a time 1 millisecond. Say at a time 90-degree. Anything you can do because your 0 to 360 degree is your AC voltage. 360-degree or 20 milliseconds. 20 milliseconds means 360 degree. I'm right. You can say in degree or you can say in time. For example, particular time, this is the way how my active power and reactive power are phase shifted at an angle 90. Now we rotate 360 degree. It will rotate only in a fixed angle 90. So you already fixed your torque and flux, or I say you already fixed your active power and reactive power. Now you rotate, you control this guy. You control this guy, its amplitude. you control active power. You control the amplitude of this guy, you control reactive. So this is the advantage of going for these transformation. So now you create a fictitious coil. You create imaginary value by using this Parkes transformation. A 90-degree, you fix it D axis on horizontal, Q axis on vertical. It's not to be like that. You rotate, what happens? Sometimes D will be Y axis, sometimes Q will be X axis in 360 degrees. It's clear to you? You rotate this one in clockwise or anti-clockwise. It's not a problem. So sometimes D will be X axis, sometimes Q will be X axis in around the 360 degrees. We have 4 quadrants. Can I go to the next one? Now this is the transformation. So I will give you next class because you should have some ideas on this equation. I will upload directly the MATLAB solution for this one if you want. Parkes, and if you are already experienced, it's fine. If you know how to do that, it's not a problem. So it's a simple matrix. If you use this matrix, this is the way how to represent your Parkes transformation. So Parkes transformation, if you feed a 3-phase voltage, you can see phase A, phase B, and phase C. And this is the frequency component, which is 001. And this is your matrix for your conversion of your 3-phase AC voltages or AC current. Anything can be the input. And the output, you get a P, which is having, you can see a look inside here. It's going to be D and Q. So you get all the variable under the control of D and Q and 0 component. So if I want to control D, I control only D. I keep Q constant. If I want to keep only Q variation, I keep D constant. This is the advantage of using this transformation. And this is called inverse Parkes transformation. So if you have all the component, again, I want to see how it is going to happen in AC. I can convert all these DQ components, which is in DC form, again back to AC form. I can use this transformation. So I'm not going inside this equation. It's very simple. If I suggest you don't go for the derivation. Derivation is available in the textbook. Don't go for derivation. You can just have a look. What is a Parkes transformation? What is Clark's transformation? So Parkes transformation, why you use? We want to convert all the 3-phase variable into again a 3-phase variable, but you can directly control your D component, Q component, and 0 sequence component. If you use Parkes transformation, your output is a DC. If you use Clark's transformation, your output is a AC. It's clear to you? Can I go to the next one? How to show your flux linkages. So this is the matrix for your flux linkages. You have now converted all the 3-phase variables into a 2-phase. I'm right. So 2 variables. One is a direct axis. Another one is indirect axis or quadrature axis. So this is called direct axis. This is called direct axis. This is quadrature axis, which is 90-degree from your D. Always fix it. It's always fixed. You rotate. It's clear to you. It is always the D and Q 90-degree, but it will be rotating in 360-degree frame. Now, how to represent your flux linkages? For direct axis, you can represent or calculate your inductance LS into mutual inductance into 3/2 LM. So this is the mutual inductance. This is the mutual flux. So you can easily calculate what is your LD. How to calculate the inductance of your quadrature axis, which is given by again LS MS minus because 90-degree. That's why you get 3/2 N. Don't look at the derivation, it's not required. Just take the final answer. If you want to make yourself, yes, if in my case, I want to be expertise, I looked all this derivation because I done my PhD. I want to do all this, but for you, for an application part of you, the final answer is important. Then how to calculate your 0 sequence inductance, because we have 3 variables, D, Q, and 0. I want to look what is the inductance of my 0 sequence components. How to calculate LS minus 2 times MS. That's it. Then I want to calculate all these flux linkages. I have the value of inductance in direct axis, quadrature axis, and 0 axis. Now I want to calculate what is the flux linkage. So this is the flux linkages in direct axis, indirect axis, or quadrature axis, and this is in 0 sequence component. Of course, I want to look at what is my flux linkages in the field excitation, because there is a winding which creates electromagnet, and this is the formula. Now, how to make it in a matrix form? It's very simple. So if you use this matrix, I can easily calculate what is my lambda d, which is the flux linkages in my direct axis. How to calculate? Look at this matrix. LD into ID plus 0 into IQ plus 0 into I0, then all is 0. Finally, I have to multiply root 3 by 2 LAF into IF. I can easily calculate. So I brought everything in the matrix. I can use a software. I introduced in MATLAB. We have a direct option to create this matrix. If you have look at my previous program, I created all the constraint in the form of a matrix. Very simplest way. Same applicable here. It's clear to you? Can I go to the next one? So this is the modeling for your flux linkage equations in terms of matrix. So I have a matrix. Only A matrix is required. Can I go to the next one? How to make the voltage equation in terms of matrix. So this is the value for your voltages to control your active power. D controls active power. Q controls reactive power. And 0 controls zero sequence component. Please note, I believe you know what is the meaning of zero sequence component. If there is a small change in impedance, you will have a difference in your voltage between three phases, frequency variations, impedance variation. All these creates unbalances. If you have an unbalance in your system, your frequency will not be 50 Hz. It has all the frequencies. If you measure that value, this is the formula, V0. So by this equation, I can able to control what is VD, VQ, V0, and my field excitation. How to calculate V0? For example, V0 will be equal to minus R into, you can use the matrix 3, 0 into IQ, 0 into R into I naught. So this is the fourth value, I'm right. So you have to third value, you have to take the third matrix row multiplied by the column matrix. You know how to do a matrix multiplication, I believe. So if you want to calculate V naught is nothing but this row multiplied by this column. Minus your flux linkages differentiation plus minus omega delta Q, omega delta D. So if you find the resultant of this matrix, you get the complete dynamics of your synchronous machine to control the active power, reactive power, zero sequence component, field excitation. As I said, we always consider balanced system. This is not practical case. It's not practical. This is only for our analysis in the system. We take all our balance. So all the resistance of the three phase are considered to be R. And omega is your angular velocity of the rotation of your machine, which is given by d beta divided by dt. Then by this equation, you can find individual values of your components of D, Q, and naught, 0, and F. It's clear to you? So this is the voltage equation modeling in terms of matrix. It's clear to you? Can I go to the next one? So generalized impedance, it's very important how to make a voltage current relationship of your complete machine. So in terms of active power and reactive power in Parkes transformation, I'm making all the three phase into a very compact system. In three phase, you all will be in three phase. The matrix is very big. But when you convert it into Parkes transform, the equation become very compact in matrix form. So this is the detailed equation. You have VD, VQ, V0, and VR. Multiplied by these components, you have to calculate into current. So this is the complete equation, control dynamic equation of your synchronous machine to control active, reactive, and zero sequence component and field excitation. It's clear to you? How to do for the torque equation? Torque equation is given by root 3 by 2 into MF, which is a mutual field excitation, into IQ IR plus LD minus LQ. So this is the inductance due to the direct axis, inductance due to the quadrature axis, multiplied by the subsequent currents. So if you use this equation, you can easily calculate what is your torque of your synchronous machine. It's clear to you? I am not going inside to the derivation. These all you have to study it in your basics of electrical machines. Same has been repeated here, but in the form of matrix. Then for a cylindrical machines, we already have known we have a salient pole machine, non-salient pole machine. So for a cylindrical rotor synchronous machine, we take always the direct axis inductance, D axis inductance and Q axis inductance, which is phase shifted by 90 degrees, is the same. same value. So your torque equation is reduced to this one. So torque is directly proportional to MF, field excitation current, and current through your Q axis for a non-salient for a cylindrical synchronous machine. For a non-salient pole machine, your torque, we call it as a torque salience, which is calculated by LD minus LQ into ID into IQ. So this is the difference based on the machine which used in your hydropower plant. If you are going to use in a rotor, which is a cylindrical one, you have to use this formula. If you are going to use your salient pole machine, you have to use this machine formula. That's it. Then how to make a dynamic modeling? How to make a dynamic modeling of your synchronous machine? To make a dynamic modeling, again, we are going inside the equation. So we know what is VQ and VD. You can have a look. This is the complete equation of VD and VQ. And this is the flux linkages due to the field excitation. And this is the flux linkages due to your generation of the output voltage of the armature. So we have two flux linkages. Then I'm going to find what is the differentiation delta F by delta T. I get this equation. Similarly, I'm going to calculate what is my delta G divided by delta T with respect to the time. I get RG into IG. So I find if there is a small deviation with respect to the time because your speed is not constant. That's why we are differentiating with respect to time. Please note why we differentiate these two into with respect to the time, because in time we have a slight variation. So with respect to the time, I find the value. Now I can able to write my equation, which is going to be reactive power control is going to be V into cos theta minus delta. Similarly, for active power, I can write theta minus delta. Please note what is this delta. This is the torque angle of your synchronous machine. How to calculate the output power of your synchronous machine? V divided by X into sine delta. If you look at the basics of your synchronous machine, how to calculate the output power? V divided by X into sine delta. So now I control my delta, I can control my active power. By controlling my delta, I can control also my active power and reactive power. Q is the reactive power and D is the active power. Similarly, I can able to control the current also, the current which controls my reactive power and active power. That's why we choose synchronous machine in power generation. Why we are not going for induction machine? Because by controlling the delta, how to control the delta? Control the excitation, the DC excitation. You can directly control your active power and reactive. Finally, I put all these in a matrix. I get a 2x2 matrix. Look at the matrix for a three-phase machine. Look at the equation for a three-phase machine for controlling the current. So big, I'm right. Now, by using transformations, we reduce the active power and reactive power control into a 2x2 matrix. And if you know the value of your armature resistance, and if you know the reactance of your direct axis and quadrature axis, you can easily control your machine. It's clear to you? We will have a break for 10 minutes, then we can have a look. Meantime, if you have any question, I'm happy to respond.